All right.
A little bit. So these first region is.
I'm sorry, I cannot hear you. So do you have a question? No? All right. Okay. So I'm gonna turn off my video first, and then. All right, let's get started. All right, share my screen here. I'm not sure. Oh, okay. So, okay, good. Seems like it's recording now. All right. Okay, so, oops. Happened again. So let me stop sharing first, and then the magic square appeared again. So let me do this again. All right, this is better. Okay, so on Tuesday, we finished the chapter 5, number 5. And so in chapter 5, we learned a lot of important concepts, definitions in quantitative genetics. And so we learned how to use very basic or fundamental, but important formulas to calculate the expectation and the variance of a random variable, right? Okay, so the last slide is for chapter 5 is here. So here we try to use the knowledge we have learned to prove what? To prove in a F2 population. So please pay attention. So this is only true for the F2 population, because in the F2 we have 3 genotypes, right? And the frequency of 3 genotypes in a F2 population is 1/4, 1/2, and 1/2. So only in this case we can have this situation. So the covariance between Z and the W. So what is Z? What is W? Can anyone tell me what is Z and what is W here?
The slope for additive effect and the slope for the dominance effect.
Yeah, very good. Thank you. Yeah, that's right. So, because this is F2, right? So in F2, so when we want to test any locus to see if this locus is sort of associated with a phenotype of interest, so we need to develop a linear model. So in that linear model, we use 2 random variables. So one is Z and one is W. So we use Z to represent the additive effect for this locus, if there's any, right? And we use W as another variable for the dominant effect, if there is any. And then we can use linear regression model to help us to test these 2 slopes to see if any of them are any of these 2 is significantly different from 0. So if we can test a non-zero, if our test detect any non-zero value for the additive effect and the dominant effect, that means this locus or the gene at this locus is contributing to the phenotype, right? So this is what we want to do. Okay, so now, so we're done with this chapter, and we know a lot of like important concepts right now. So then we can move forward to use the knowledge we have learned so far to detect the major gene effect. All right, so this is the logic behind between the chapter 5 and chapter 6. Okay, now, so remember, so in this chapter, we want to test the signal. We want to test what is the signal. Here, we want to test the association signal between any locus and the phenotype. All right, so I use this diagram to help you understand what is going on behind the test. So last time I mentioned, for example, this is a chromosome, and we have a lot of markers or loci along this chromosome, right? So we want to see if any of these loci is contributing to the phenotype. Let's say Y. Okay, Y is a specific phenotype or trait we want to study. So, for example, if we are talking about a trait in rice, for example, the most important phenotype in rice is the yield, right? So we want to find the genes, genomic loci that are contributing to the rice yield. Or if you are studying a human genome, so if you are studying, like, for example, a cancer, breast cancer or prostate cancer, so you also want to find, so first, in a specific cancer, you have different phenotypes. For example, the aggressiveness of a tumor, a type of tumor. So if you treat the aggressiveness of a tumor is a quantitative traits, then we can still do the same thing. We can scan the genome. We can test each locus on the genome to see if there's association between the variation in this locus and the variation in the cancer phenotype. So the same thing. All right. So suppose we want to test each locus to see if each locus is associated with this. Then we can test this locus first, right? If there's no signal, we can move on one by one, and until we complete the scanning along this chromosome, right? Okay. Oops. Jeez. What happened? Let me see. Okay, that's fine. All right, so now suppose this is the results we have. So for most of the loci, you do not have signal, but for some specific loci, you got a high signal. And then again, no signal, but some random noise moving the curve here or there, and then another peak, another signal, right? So, okay, so if you scan the genome and get this graph, so this will indicate, okay, oh, wonderful. So we identified, on this chromosome, we actually identified two loci that are potentially associated with the traits of interest, right? So this is what we do. So here, so how can we detect this signal? Or if we see a peak, how can we prove this signal is a real one, but not a fake one, right? So here, so I would like to borrow some concepts from engineering. So they like to use this thing to help them detect the signal. So they always compare the detected signal with the background noise. So to form this ratio, so I believe they define this ratio as a signal to noise ratio. And so if this ratio is significantly greater than something, for example, than 1, which means, okay, the signal you detected is significantly greater than the background noise, then there's a strong evidence or confidence that you believe this is a signal, not a noise, right? But if this ratio is close to 1 or even less than 1. So you do not believe this signal is real one. So you're gonna say, okay, this is not a signal. So in statistics, we do the same thing. So while we have a data, if we want to test if a association is a real or not, so we can use our data to construct it. So this is what we have learned in chapter 5, right? We can use our data to construct a statistic, which is defined as the ratio of the estimate. So suppose we want to test if B1, sorry, this is a slope. We want to test if B1 is a real or not, or if we want to test if B1 is significantly greater than 0, indicating a strong association, right, between the locus and the phenotype. So first we can get the estimation of the B1. That's the estimation in the numerator. And also we can calculate the standard error for this estimation. And we use this tool to form a ratio. This is called the statistic. So the same thing, if your estimation is significantly larger than the standard error, then that's a strong evidence to show, yeah, this B1 is real, not equal to 0. And this will indicate a strong association between the locus and the study and the phenotype of interest. So any questions? This concept is very important. Ooh. Why cannot, I don't know why I cannot. Let me stop share first. I don't know why I cannot remove the marker here. So don't save, okay. Sorry about this. Okay, problem solved. All right. Okay, so any questions? This is very important concept. I hope everyone can understand this very well. So you will feel comfortable in the future about the test. All right, so here, so for example, yeah, so this is what we do, right? Because this is the real signal, but when you use some instrument, when you use some machine or instrument to measure this signal, so sometimes the data you got involves some noise, background noise. So what you will get from your experiment is a combination of the real signal and the noise. So that's this. So this is the reality. So you got the data like this, but you need to figure out a way that you can test if the signal buried in this noise is a real one. So that's why in engineering, so they construct this thing like the signal to noise ratio. But in statistics, we use this. We use this thing called the statistic. And this statistic is calculated from your data. And so this ratio, the numerator is the estimation of the parameter of interest, for example, the slope, B1, and the denominator is the standard error for that estimation. So you use this as an evidence to complete your hypothesis testing. And this results, the testing results will tell you if there is association between a specific locus and the phenotype of interest, right? Okay. Let's move on. Okay, now let's go back to our business. So we try to use the linear model to help us to detect the signal or the association, potential association between any locus and the trait of interest, right? So let's start from the easy one, the backcross. design. All right, so the backcross design, so either this one or this one, right? And we only have how many genotypes here? So actually in a backcross design, so in any backcross design, we only have 2 genotypes here, either A1A1 or A1A2, right? That's the backcross. All right. Oops. Let me remove this. Sorry. Okay. So here we use this regression model to help us to do the test for any locus for a backcross design. So here, there's a special thing here I would like to point it out at the first, because in a backcross design, so we only have 2 genotypes, right? So this 2. So we do not have another parental type, right? Because this is a backcross, not a F2. Then some information is missing. So that's why in this regression model, we only assume there's an additive effect. Even there is a dominant effect because of the missing data, we cannot estimate that dominance effect. Or in another way, we can say, in statistical way, we can say the dominance effect is it cannot be estimated. So this is the way we said it. All right, and so in this case, as I mentioned, we use a very simple regression model to help us to describe the relationship between the phenotype and the genotype of a locus, all right? By assuming there's only additive effects. So this is a very simple linear regression, right? So we have a y, we have an x variable. Here we have a mu is the intercept, and the a additive effect is the slope. So, and then we can easily fit our model to do the analysis. So any questions here? Do you have any questions about this setting?
Yes.
Oh, yes, go ahead, right? Yeah, let me remove this. Yeah, go ahead.
So what is the value for the mean again?
Oh, you mean this?
Yes. What is the value?
Okay, sure. All right. So if you so if you recall the stuff we learned in chapter 5, so we have something called the midpoint and the additive effect and the dominant effect, right? So just like this. So this G11 represents the expected value for the expected phenotypic value for the first genotype. If we assume the A1 is the first genotype, and this is the third, the expected phenotypic value for A2, right? So the midpoint is defined as the mu.
Okay, I got it.
Okay, yeah, very good. All right, so the A additive effect is the difference, is defined as, so think about this. This is A or G22. This is G11, and here is G, this point is the G12, right? So this genotype, the difference between genotype and the middle point is defined as the additive effect. And this difference is defined as the dominant effect, right?
Mm-hmm.
I have a question.
Yes, please. Yeah.
So for the backcross experiment, there is no J22. So can we still calculate mu and A and mu and A.
Yes, mu and A. Yeah, this is what I just mentioned. Yes, of course, we can still calculate. Good question. So let me remove this and refresh this slides. Okay, so here, as you can see, because so for example, in this backcross design, we are missing the value from this genotype, right? So
Yeah, so we don't have the quantitative
value.
result for the value for A22.
That's right. So that's why when we use this model, so this actually, so I think, yeah, it's better to put a star here. So this mu star and A star. So if you use this linear regression model and use only the data from A1, A1 and A1, A2, you can estimate the mu star and A star, but not real mu and A. Why? Because here, all right? So this is the mu star you can estimate from the model. And this is the A star calculated from the model. And the mu star is actually equal to the real mu plus the dominance effect. And the A star you estimated from data is actually equal to the real additive effect minus the dominant effect. That means because of the missing data, so the D is not estimate, D cannot be estimated. So what happened is like the D value will be absorbed in the mu star or in the A star. So in statistics, we have a specific term for this confounding factor. So in this case, because of the limited data available, so the D is actually confounded by the other two parameters. So you cannot estimate D definitively. So yeah, that's a good question. I hope I didn't confuse you, because yeah, this is a very very difficult concept in statistics. But I hope you intuitively that makes sense, right? Because of the incomplete data, so something because the data is incomplete, so there's a cost for the incomplete data, so which means you have to sacrifice the estimation of some parameters, for example, D. All right, so in this case, we put star on the mu and a star on the A, and the model you used here to analyze the backcross design can only gives you a approximate estimation for mu and A, but still that is good. That is good, right?
I have a question.
Yes, please, Livy.
Yeah. Why do we assume 1 or 0 for xj or +1 or -1 for xj?
Oh, okay. So you mean this too, right?
Yep.
This, yeah, okay. So yeah, actually, so when you use this model to do the analysis, so we have our own option to define this X random variable. So one way to define the X is the genotype, right? The variable that can be used to represent the variation from the genotype at this locus. All right. So one way we can define the xj is using 1 or 0 to represent these two different genotypes, right? So
Okay.
look at here. So what is this? So if maybe I should draw this. Okay, so here we only have like G12 data and G11, right?
Right.
So if you look at here, so if there's no, so we do not assume there's a dominance effect. What is the consequence by that as assumption? So if we assume there's no dominance effect, then this locus is a additive locus, right? So the G12 should be equal to the midpoint, right?
Right. Yep.
Okay. Now, what's the difference between G11 and the G12? it's A, right?
Mm-hmm.
Okay, now that's easy. So if this is true, so what is the model here? So if for example, if we are talking about a individual with the genotype like A1 and A2,
Mm-hmm.
so the value of that is just equal to mu, right?
Right.
Then
Yes.
how can we deal with this additive? We put a 0.
Zero.
So the 0 times A plus this.
That will
This
get
is the
0.
genotype for this, right? If we look at the genotype for A1 and A1, so it is equal to mu plus A, right?
Mm-hmm.
But how can we deal with this X? We put a 1 here times.
Oh,
So
okay.
this is the way how we define the random variable to facilitate using the linear regression model to help us to describe the relationship between the genotypes and the phenotype.
Okay.
Is that clear?
Yep. Yep.
Okay.
Got it.
Very good.
Thank
very
you.
good. Mhm. Any other questions? Okay, so there's another way. Actually, there's another way. So Nivi just asked the question. So this is I just mentioned. This is the first option to define your X, right? There's another option to define your X the same way. So if you define the X equals to +1 for the first genotype and a -1 for the negative genotype. So what happened is here. So let's say A11 equals to mu plus 1 times, let's not use A, let's use use another thing, let's say beta, okay? And A12, we are talking about here. So in this setting, so A12 is what? Can anyone tell me? Minus, right?
Minus beta.
Yeah, minus beta. So if you use this model to calculate this, actually beta is equal to 1/2 A, right? The same thing. So here, if you use this code to represent the genotype of A1, and A1, A2, so using the same regression model, now beta. So then when you estimate the beta, the estimated beta is actually just 1/2 of the original additive effect. So this doesn't matter, right? So that's why we can arbitrarily define your own random variable to fit the regression model. But there's a linear combination of the estimation, the new estimation and the original estimation. So any questions? Okay, good. Okay, now, okay, since we have this model and we have the data, we can plot the data. So suppose this is the genotype, and this is the phenotype, and we use a regression model to summarize the observed data, right? So last time we learned we can use a least square to find the best regression model to describe the relationship between the X and Y, right? So least square estimation. And okay, so now when you get your estimation of beta, so what is B here? B1, let's say. Is the slope, right? Any questions? Okay, yeah. So what kind of slope can indicate the evidence of association between a locus and the phenotype? Either this one or this one, right? But not this one. Why? Because this one, the data says the slope equals to 0, which means there's no association between x and y. Only one b0 is not, only one b1, the slope b1 is not equal to 0. Then this indicate your genotype is associated with your phenotype. Do you agree? Do you agree? Questions? Yes, please, questions?
So we're talking about slope. So we're talking about just basic, is there a positive or negative relationship or association between?
Yes, yes. Because let me try to link this to you. So go back to our model I just showed you. R8, this is a, sorry, plus error. So this is the model we used for the back cross design, right?
Mm-hmm.
So this is the phenotype, and this is the genotype, and this is the midpoint, and this is the additive effects, right? Is this a linear regression model? Of course. This is a linear regression model to describe the relationship between y, which is here, right? Y, and the x, which is the x genotype, right? And so using this model, we actually test whether this slope here, a is the slope, right? We want to test if a equals to 0 or not. Just like this 3 situations, right? Is that right? So okay, so if we are looking at a specific locus and the data tells us a equals to 0, what does that mean? That means your data should look like this, or it means that this locus is irrelevant to the phenotype you are interested, right? However, if when you analyze another locus and the data at that locus gives you a positive A value, what does that mean? That means like the way you define the first genotype and the second genotype and the third genotype. So that gives you a positive association between the genotype value and the phenotypic value, right? And if you move to another locus, and that locus will give you data like this, which means what? Which means what? Means the way you define your genotypes, the first genotype and the second genotype and the third genotype is negatively associated with the phenotypes, right? Okay, so only the first situation and the third situation indicate the association between the locus and the phenotype, but not the second one, right? So this is why, so when we do the GWAS, when we test each locus on the genome, we want to test this slope. We want to test if the slope associated with this locus is equal to 0 or not. Is that clear? Mm-hmm. Okay, very good. Okay, so yeah, so easy. So we just translate our language, so translate the biology language into the statistical language, right? So in biology language, we want to test if the locus is associated with the phenotype. But if so, this language translated to statistic is okay. So we want to test for this locus if the slope is equal to 0 or not. Okay, so least square estimation in quantitative genetics. So as I mentioned, we use this regression to test each locus in a backcross design. In the backcross design, we only have one slope because we assume the dominance effect is gone. There's no dominance effect, only additive. So we only deal with a single slope. That's easy. So this is equivalent to this. I just show you this equation, right? And in the least square, so we use this formula to estimate the B1. So why do we need to estimate the B1? So by the way, I try to make you to think about the previous stuff we learned. So why do we need to estimate the B1?
Yeah, we want to know we want to know the relationship between the genotype and phenotype.
Right. Very good. Thank you. So because if we want to know the relationship between the genotype and the phenotype, so we need to construct a statistic for this locus, right? And the statistic consists of two parts, the ratio of two parts. One is the estimation of the slope, this, and the other one, the denominator, is the standard error for this estimation, right? So once we have this tool, so we can easily do the test. So that's why we want to estimate this. And the least square estimation gives you a beautiful estimation of this guy, the slope, right? The formula is terrible, but you don't worry about this. So I don't require you to memorize this, but you need to know, okay, so this is the formula that we use to calculate the least square estimation for the slope, of this linear regression model. All right, this is how we calculate the B1. So the mu, we use this model, we use this formula to calculate the estimation for the intercept. And this is how we calculate the residual error variance, because we need to use this to calculate this. So we need to calculate the residual error variance for the further calculation of the standard error of the estimation of the B1, right? Okay. Okay, so now for the linear regression model, so totally suppose we have like n observations. So can anyone tell me what is n observations means what? We are talking about
number of the progeny.
Yes. So we are talking about, very good. We are talking about a backcross, right? Backcross design. So in this design, we can generate this many progeny, right? And the n represents the number of the progeny that are available for the analysis, all right? Because you have n pieces of the independent data for analysis. So initially you have n degree of freedom. However, when you do the estimation using this model, there are a total of two parameters that you need to estimate, right? So when you use the data of n degree of freedom to estimate these two parameters, then you lost 2 degree of freedom. That means like finally you only have n-1 degree of freedom. So this is another important concept. You need to use these concepts to find the right numbers in the either the chi-square table or the t-test table to find the right critical value for your test based on this degree of freedom. Any questions? Degree of freedom? Have you learned this concept when you take any statistic classes?
Yes, a little bit.
Okay, good, very good. So basically, how do we calculate the degree of freedom? So if you do nothing, you just have a pure data, then the number of independent data point is the degree of freedom. So for example, here, if you collect n progeny from the backcross design, you have n pieces of independent data point. Then the initial degree of freedom is n. If you use this data to do the calculation, where you estimate the two parameters, right? B1 and B0 and B1, then you cost the 2 degree of freedom. So finally, you only have n-1 degree of freedom. All right, very good. Okay, so I think before the class, I upload some example code to the iLearn. So right now I'm going to show you an example how we do the linear regression model in R. Can you see my screen?
Yes.
Okay, thank you. All right, so first, let's define X. So you use this command line to generate X. So here we generate 100X to represent 100 genotypic value for 100 progeny from the backcross, right? All right, so this is the X. So here I don't use the 1 0 1 0. I just because I use a general case. Here we just generate like 100 value evenly distributed from -1 to 1. So we have this many values. And okay, now suppose we let the B0 equals to 6 and the B1 equals to 3. And then we generate 100 random error, which are normally distributed with mean equal to 0 and the variance equal to 1. So by doing this, by following this code, actually we can learn another skill from this class. So we know how to use computer to generate your own data. So this is called the simulation. So in the future, when your research is involving some simulation study, so now you can learn how you can use computer to help you generate some pseudo data here. So suppose first we generate the pseudo genotypes for 100 individuals. Now we set intercept equals to 6 and the slope equal to 3. And finally, we're going to generate 100 measurement error. So we use this command line to generate 100 errors here. So what is E? So E looks like this. If you plot the density of E, you're going to see it's roughly normally distributed, right? Yeah, that's a normal distribution. Okay, now you combine these things together. So can anyone tell me what is this? If we do this, what is this?
Linear
This-
combination of the variables.
Yes, so we have intercept here, right? We have the slope additive effect multiplied by the genotype and plus the random error. So here we use this linear combination to simulate the phenotypes for 100 progeny. Does that make sense? So this is the way we can use computer to generate data, fake data or the pseudo data for your simulation study. So this is another skill you can learn from this class. I hope. I hope this will be helpful in your future research. All right, so now we have X and we have Y. So let's see what's the relationship by plotting these two random variables. Let's see what's the relationship between them. So clearly you see some trend there, right? All right, so suppose this is the data. So this is totally the simulated data. So you can follow this code. You can just follow this coding to generate your own data. So this is the data I just generated. So you can see clearly there's a trend between X and Y, right? So now how can we get the estimation of slope or the intercept from this data? So we have learned, right? So we can use the least square estimation. Do you still remember? So if we have the data, we can use the least square estimation. So you don't have to memorize how the formula is formed, but you can use computer to help you to analyze this data. So here this line shows linear model. LM means linear model. You try to fit a linear model by regress y on x, and this will gives you the least square estimation. What is this? Can anyone tell me? Look, by comparing this, okay.
X is B2?
Yes, B0. So
B0,
X
sorry.
is B1. Sorry, X represents
X,
the coefficient associated
like the
with H.
intersect.
Yes, so the intercept is here. 5.8. It's not bad, right? It's close to 6. And the B1, actual B1 is equal to 3. So by doing the least square estimation, yeah, it's not too bad. 3.2. Very close, right? Because of the random error. Because in this simulation, I put the random error in the data, right? So this will make the existence of this random error will make it impossible for you to estimate the 100% accurate estimate of your parameter, right? So that's why, because of the existence of this error, so you can only estimate a value which is very close to the real value. So this is the case, right? So based on this noisy data, so we can still find the very good estimation for these two parameters. One is the intercept and one is the slope. Is that clear? Any questions? So in the final exam, I may give you an example question like this, and I'm gonna give you some data without giving you the number of the B1 and the B0. So I'm gonna ask you to run this code and find the solution and perform the statistical test on the slope for me. Will this be a problem? Okay, very good.
As long as it's a basic linear regression.
Yes, this is very basic linear regression.
We're not doing anything like multivariate.
Not so multivariate means like we have multiple y's. Probably you refer to the multiple regression, right? Multiple regression means like we have a single y, but we have multiple x. We do, yeah, because when we talk about the F2 data, so you see we have 2. So this is the maximum. So I'm not gonna test you beyond the 2 parameters, beyond the 2 slopes. Sorry. Okay.
And so here comes the Z and W again.
Yes, yes. So here, so I just use one slope. So think about this B1 as A. So that's the additive effect only. So we use this model to test the backcross design, right? But here, look at here. So this is F2 data. So now we have both additive effects and the dominant effects. And the Z is the random variable for the additive effect, and the W is the variable for the dominant effect. So now in this model, so this is called the multiple regression model, not the multivariate. Multivariate means like here we have multiple Y. So that's the multivariate. But multiple regression means like still we have a single phenotype Y, but we use different predictors here in the same regression model. Does that make sense?
Yep.
Okay. So yeah, you use this to get the estimation, and you can use this common 9 to test the slope. So if you run this, this will give you the test p-value for the slope. So here, so this is the F value. So we're going to talk about this because when we want to test the B1, which is the slope for this linear regression, we want to construct a F statistic. And this is the value for the F statistic in this specific case. And this is the p-value, which is associated with this F test. So we have learned about the p-value, right? So when we talk about the hypothesis testing, the p-value means what is the chance the p-value means given your null hypothesis is true, what is the chance you're gonna observe the data like this, right? So that's the p-value. All right, so can anyone tell me what is the null hypothesis in this situation when we use this linear regression model to test the association between a locus and the phenotype?
No association.
Slope is 0.
Yes, very good.
Mm.
You guys are great. Right, so yes, this is simple concept, but it is very important. So no matter what kind of statistical testing you do, no matter in the future in your research, in your own research, what kind of hypothesis you want to test, we usually put the easy one, no signal, no association on the null hypothesis, right? We want to test that. If the p-value is extremely low like this, which means the data is unlikely to support your null hypothesis. So you're going to reject the null hypothesis. So in this case, we believe there's a strong association between X and Y, right? If you look at this data. So even without testing, you can tell there's association. But the test, the statistical test, will give you some numerical evidence. Then you can publish your data without problem, right? So any questions here? Okay, very good. So this is actually what is happening behind the R code I just showed you. So in the R, so we actually use this model, regression model, to test whether the slope or the additive effect is equal to 0 or not, right? So the null hypothesis is, okay, additive is equal to 0, but the alternative is no, the additive effect is not equal to 0, which indicates a strong association between this locus and the phenotype. Now we just put the null hypothesis on the test, on a trial, to see if data fits this null model. So then the R code can help you to calculate the estimation of this B1, the slope, and also can calculate the variance of the estimation of B1 to construct a F statistic for the test. All right, so this ratio is equivalent to this, right? Does that make sense? So we try to construct the F statistic, which is a ratio of these two. This is actually the ratio of the estimation divided by the standard error. Something like the signal and noise ratio, right? Any questions? Okay. Okay, so this is the distribution of the F. This is the example showing different F distribution when the degree of freedom with different degree of freedoms here. All right. So suppose this is the value, the F value you calculated from your data. So if this value is larger, this will give you small p-value. And in another way, so if you calculate the F value and the greater the F value, the smaller the p-value, and then so you're gonna reject the null hypothesis, and this will give you a strong evidence to show the association between the locus and the phenotype. So any questions? Any questions so far? Good, very good. Yes, go ahead.
So for DF1, DF2, why there is 2 DFs? Like,
oh yeah,
degree of the
okay.
freedom?
So this is general. So maybe I can show you this slides. So, okay. So this is a general, let me see. So this slide actually shows the relationship between different distributions, like how you can relate the F distribution with the chi-square distribution or other distribution. So
Mhm.
in our case here, the degree of freedom always, the degree of freedom 1 always equal to 1, because here we just test one
Mhm.
one parameter, right? And the degree of freedom 2 equals to n
And
minus 2.
minus
Yes.
minus 2. Okay.
Yes. So but here I just give you a very general idea. So if you have different numbers for degree of freedom 1 and 2, so what do the distribution look like, F distribution? But in this case, if we only talk about the backcross, if we only tested a single slope, so you always use the F distribution. The first degree of freedom equals to 1, but the second is n minus 1, n minus 2, sorry. Okay, yeah, good question. Yeah, when we talk about the more complicated design like the F2, so we're gonna see change in this of degree of freedom. All right, very good. Okay, so this is the table I just mentioned, right? So when you want to manually do the calculation, but now, so this is old-fashioned. Right now we don't, so I haven't been using this kind of table for years, because if you use R, so R can calculate the values for you. But I think still when we teach the class, still this is useful, because when you manually get the data, calculate the values for your test, using the manual way, so that can help you better understand the theorem behind the calculation, right? So here, since the first degree of freedom always equal to 1, because we are just testing a single slope, so we only look at the first column, which represent the degree of freedom equals to 1, right? For the first degree of freedom. And for the second, so this table is for the alpha equals to 0.05. So if you want to test a test slope by using alpha equals to 0.05, so you just look at this table and just look at the first column, but you may have different number of progeny, right? So suppose if you only have like 20 progeny for your study, so you're gonna look at the second degree of freedom equals to 18, right? If you generate another study which had more progeny, for example, 30 progeny, then n minus 2 equals to 28. So for the second degree of freedom, you're gonna look at here. And these values are the critical values. So can anyone tell me where, in what situation we can use these critical values identified from this table to help us make a conclusion for your hypothesis testing? So what do we need these numbers? So can anyone tell me? So why people? So this is a very useful table, right? Because why is that? Why? So where do we use this table for to facilitate our testing?
Do we compare it to the F statistic?
Yes, very good. Thank you. Yeah. So these are just the ruler, right? This ruler gives you some criteria. So you use these numbers, so-called the critical values, to compare to your F statistic calculated from your data. So by this comparison, you can get a p-value, right? And the p-value can tell you either you should reject your non-hypothesis or in another way, right?
Mhm.
Very good. Thank you. Okay. So as I just mentioned, so I don't want to spend too much time on this because maybe not most of you, not everyone of you are interested in this, but if you are interested in this, so you can spend some time, extra time to check the relationship between different distributions, for example, here. So how we can relate the chi-square distribution with a F distribution, something like this. Because chi-square, we only have a 1 degree of freedom, right, for each random variable. But when we construct a ratio for these two chi-square random variables, then we have 2 degrees of freedoms here. All right. So, okay, so we are done with the very basic design backcross. Now we're going to deal with some more complicated case, F2 design. So now we have the information for 3 genotypes, right? We have data for all 3 possible genotypes here. Okay, then what is the results? So since we have all the data, so we can afford to estimate both additive effect and the dominant effect, so, which is good. So that's why, so because F2, yeah, will cost you more, either the research fund or the efforts. But since you paid more, so you're supposed to get more return, right? So this is the return. So since we are using more complicated design, the F2 design, then in this case, we can estimate both additive and the dominant effects, right? The same setting here. And now we use this regression model. This is called the multiple regression analysis. And we use the same way to define the Z variable, right? So the Z, random variable Z, is used for additive effects, and the random variable W is used for the dominant effect. Look at here. So for the first genotype, we only have the additive effect, but not the dominant effect. So that's why for the first genotype, the Z equals to 1, but W equals to 0, right? If you look at the second heterozygous genotype, the second genotype, in that case, there's no additive effect, but only a dominant effect. So that's why you see a 0 for Z, but 1 for W, the same for this one. Any questions here? And also the ratio for this, because we are talking about a special design, the F2 design, the ratio of these 3 genotypes is 1 to 2 to 1. Any questions? Okay, good. So the same, right? We have multiple regressions here. We have more than one slopes to estimate. Then we can write a B vector. This is the parameter vector. We have 3 parameters now. So still B0 represented the intercept, but now we have 2 slopes here. Okay, one is for the additive effects. The other one is for the dominant effects. A, D, okay. All right, this is the X. Actually, so for intercept, this X is always equal to 1, right? So we don't worry about this. Actually, the first X random variable is Z. We just replace this using XJ1 to write a X matrix here. And the second random variable is equivalent to W. So we use these two for the additive effects and the dominant effect, respectively, right? And still we use the least square estimation to estimate this beta vector using the matrix notation here. So this is the estimation for the 3 parameters. This is a vector, and this is the matrix notation here. This is also the least square estimation, and also we can estimate the estimation. We can estimate the residual variance here. So this will help us to calculate the variance of the beta estimation to construct a F statistic. Any questions here? Very good.
One
Yeah, go
question.
ahead. Sure.
What is B naught again?
B naught. Okay. Sure.
Which one
Okay.
is-
So here, right? So this is equivalent to mu,
Okay, I got it.
midpoint, intercept. Yeah. Okay. So look at here. So this actually this because in writing we so this is the common way we write a regression model, but actually this is equivalent to this, right? So this is more straightforward when we talk about a association, a genetic association study. So when we talk about a single locus analysis, so this is easy to understand, but this is the same. We just replace these things by different names. So the B0 means the intercept. All right, any other questions? Okay, good. Okay, now the same, right? Because we're talking about this. We have two slopes here. So the null hypothesis is okay. Both of them are equal to 0, which means there's no association between this locus and the phenotype, right? So this is easy to understand, right? And the alternative, there are a couple of ways to define your alternative hypothesis. Either maybe the additive effect is equal to 0, but there's a dominant effect there. Or the other way, if dominant is, there's no dominant effect, but additive effect is real, right? Something like that. So either way, so we can test this hypothesis. And all right, so as I mentioned, how do we test this? We use least square estimation to estimate this beta, and we can calculate the variance of this estimation, and then we can construct a F-test to test them both. This becomes this F-test. Now look at here, because we are testing how many parameters here? We're testing 2. So in backcross, we only test 1. So that's why the first degree of freedom equals to 1. So that's equivalent to the chi-square test. But now, since we are testing 2 slopes simultaneously, so here the F test, the degree of freedom, the first degree of freedom of this F test becomes 2. Does that make sense?
Yep, makes sense. 2 parameters,
Okay.
therefore 2 degrees of freedom.
Yes, yes. So, okay, so if you don't think that the case will go that crazy or that complicated, so you can still test 1. So in this case, you can just test additive, or you can just test the dominant. So this will gives you what, like this, the regular test, right? So this will gives you the 1 degree of freedom here. So why is here? So why the second degree of freedom equals to n minus 3? Can anyone tell me? Because we have n data points, right? That's the initial degree of freedom. But here we estimate how many parameters here? B0, B1, and B2, right? Then this will cost us 3 degree of freedom. So finally, we have n minus 3 degree of freedom. Is that clear? Okay, good. All right, so before we move forward, let's give you an example. So, okay. Okay, so here, so you can see my screen, right? Okay, so this, the first example, just give you a very simple linear regression analysis. Now, so let's learn something new. So we can use computer to help us. So this is the beauty of this course. So we can learn different skills. So hopefully this will be helpful in your future study. So you can use computer to help generate your own simulation data, right? So here, okay, suppose we're talking about a F2 and F2 population. So first we're gonna generate 3 genotypes because we knew this is a F2, right? So the first genotype will take 25% of the progeny, right? The second genotype, which is the heterozygous, will take the 50% of your population. And the third genotype, which is A2, will take another 25%. So in this case, you generate the label for this 100 individual. So you're gonna see what? The first 25 represent the first genotype, the second 50 represent the second genotype, and the last 25 represent the third genotype. Okay, this is how we generate the Z and the W for this population of 100 F2 progeny. And in this case, we let midpoint equals to 6, all right, midpoint. And additive effect equals to 3. So can anyone tell me what is the expected what is the expected phenotypic value for G11 based on this? G11 is the highest one. G11 equals to the midpoint plus the additive effects, right?
9.
So in that,
9.
yeah, 9, yes. How about the G22?
3.
Yes, very good. Thank you. How about the G12? So if we define the dominant effect equals to 1.
7.
Yes, very good. You guys are great. I'm so happy. Yeah, okay. So this is the parameter. These are the real parameters. Okay. In the final exam, I'm going to use the same thing, not the same number, to generate some data for you, but without giving you these real numbers. You still can run the program to estimate these numbers. Can you? Okay, so this is, suppose this is the real case, but now we're gonna introduce some difficulties for your data, right? So we're gonna bring in some random errors here. We still generate 100 random error from the standard normal distribution. So if you plot this density, you're gonna see this is a normal distribution. Yeah, roughly a normal by model. That's fine. Okay, so what is this? Can anyone tell me? If I run this?
The multiple regression model.
Yes, so I generate realize the phenotype values for this 100 progeny, right? Okay, let's look at the data. So what does the data look like now? If we combine this data, so this is the 100 of progeny we generated. So the first 25 represent the first genotype, and the Z for them is equal to 1, right? That makes sense. And the W means for the first 25, there's no dominant effect. Okay, for the second 50 individual, which represent the second genotype heterozygous, so the additive effect equals to 0, but the dominant effect equals to 1. The W equals to 1 to represent the existence of the dominant effect, right? Okay, now for the last 25 individual, this represents the third genotype, which have the minus 1 additive effects, right? So that's why Z equals to minus for these guys, but dominance effect gone. So that's why we put W equals to 0 for the last 25. Does that make sense? Does that make sense too?
Yes.
And okay, thank you. So those are the realized phenotype value. Those are the data you can get from your from doing the experiment. But this data are the combination of the real signal and the noise, because we purposely put the noise in the data. Is that right? Okay. So hopefully, yeah, by doing this, you know how to generate your own simulation data in the future. So this is a very useful skill. Okay. Okay, let's look at here. So if we plot Z versus Y, so you see, right? Clearly there's the association. So for the first genotype, second genotype, and the third genotype, this is the third genotype actually. This is the heterozygous, and this is the first genotype. You see clearly there's a trend between the additive effect and the phenotype, right? But when you plot the relationship between W and Y, so it's not that clear, but still you see difference, right? The three groups here, all right? So then you can use the same linear model analysis to estimate this. Oh, not too bad, right? What's the real number here? Let's see. Not too bad. Do you agree? Very close. Okay, so because we only have like 100 data points, that gives you such accurate estimation for 3 parameters. Imagine if you have like money to perform a extremely large experiment. Suppose you can generate like 100,000 projects for your study, then you can get a very good estimation which are very close to your real parameter value, right? Okay, now you can make the test, right? See? So now in this table, so this is the ANOVA table. So we use ANOVA to test the dominant, the additive effect and the dominant effect, which gives you the p-value this and this, which means what? Can anyone tell me? This means what? This means, okay, yeah, this locus is associated with the phenotype, right? And both effects, both additive effects and the dominant effects exist to affect the association between this locus and the phenotype. Is that clear? Okay, I hope this is clear. And I already uploaded this code, this R code to the iLearn. So please, yeah, try running this code by yourself when you have time. Make sure you understand them, because this is most useful not only for our test, but I hope like in the future this can help you to design your own in silico analysis. Because yeah, by doing this, you can generate your own simulated data for some study. All right, I think time is up for today. And so any questions so far for today's stuff?
Yeah, one clarification back on the code.
Okay.
G12, it's going to be midpoint plus dominance effect minus additive effect to equal 7 for the values you assigned.
Oh, you mean here, right?
Yeah.
Okay, so all right, mu, yes, exactly. So if you look at the previous slides about the definition of these 3 things, so mu is actually at the midpoint between the first and the third genotypes, right? So here, midpoint is if midpoint equals to 6, but additive equals to 3, which means the first genotype, let's say the first genotype is associated with the higher phenotypic value. That means like the G11 equals to midpoint plus A, that's 9. And the third one, which is associated, G22, which is associated with the lower phenotypic value, should be 6 minus 3, that's 3, right? If there's no additive effect, the midpoint mu should be identical to G12, which is 6. So if there's no dominant effect, then your G12 should be equal to 6. But because of the existence of the D, the dominant effect, so your G12, real G12 is not identical to the midpoint. So the difference between them is defined as the D, the dominant effect. Right now here, for example, in this case, which is 1. So that means the real G12 in this case should be 6 plus 1, which is 7. Right?
But then where's the additive effect? Is it included at all in G12?
Oh, the G12, there's no additive. There's no
Okay.
additive.
Got it.
Yeah. So if you look at the definition, the G12 equals to mu plus D, right? Mu plus D. There's no A there.
Got it.
Mhm.
And then of course G22 is going to equal to 9 again.
Yes. No. G22 means equals to 6 minus 3 because there's a minus 1 there, right? G22 equals to 6 minus 3. So that should be 3.
Okay, so it's midpoint minus additive effect.
Mhm.
Okay.
Does that make sense?
Mm-hmm.
Cool. All right. So when you have time, please, run this code, and make sure you understand. It's not that hard. It's easy. Try to understand the meaning for each step. So if you have any questions, just send email to me, or we can discuss. Today in the afternoon we have an office hour, right? So if you have any questions regarding the knowledge we learned from this PowerPoint slides, or if you have questions about the coding, let me know so we can discuss. Questions? We still have time, so we can yeah, if you have further questions, we can discuss now.
I have one.
Yes, go ahead.
So is there any possible for the D equals to a negative number?
Oh yes, of course.
Okay.
So even that is true. So if you change the rows of G11 and G22, so still you can't. So it's very arbitrary. So totally depending on how you define the G11 and G12, G11 and G22. So if you the current setting, if G11 sorry, I take this back. Yes, so we always put the genotype, the pure genotype associated with the higher phenotypic value as G11, and the lowest one is the G22. But if you see difference from the G12 and the midpoint, this difference could be positive, like this one, or could be negative. Yes, sure.
Thank you.
Yeah, no problem. That reflected the different kinds of interaction between these two alleles. When these two alleles come together to form a heterozygous genotype, yes, it could be negative. So you can try different ways. So those are the numbers I gave you, but you can try different ways to do that. Yes, very good. So any other questions? So for our coding, so this is the standard. I'm gonna require you to use R. So it's not that hard. So I will not ask you to do the GWAS using R for me. So, but hopefully, like, but I think I'm thinking about, like, I have a postdoc who is very experienced in doing the GWAS analysis. So maybe next month, sometime I can invite him to give you some real case to show how in real life, in your real, like, a research life, how you can use advanced statistical and analytical tools to help you to do the GWAS, to find the genomic loci that are associated with the trace of interest. So I'm gonna invite him and ask him to prepare some good examples for you to show you how we can use that to do more advanced research on this topic. All right. So if you do not have any questions, so we're gonna stop here. And, yeah.
I have one question. For the exam, will you ask for our code?
Yes. So because everything is electronic, right? So even you type your own code, so you can copy and paste.
Okay.
Yeah. On the so I will ask you to. So I'm gonna put the questions on a Word file, and you can type in. So for some, let me think. Yes. So you can type in, or when there's some like calculation needed, so you can grab a piece of paper and write your calculations and take a picture and put the picture on the Word file. And finally, you just compile a single Word file, including the R code and the R output and your picture showing your calculation, and send it to me, I think.
Okay, sounds good.
Sounds good? Yeah, this is the beauty for the current technology. So we can easily handle that. Yeah, good question. Thank you. Please. All right, any other questions? All right, good, very good. So so yeah, we're gonna have a office hours in the afternoon. So in case you have question, yeah, I'm gonna see you there. All right, thank you. Bye-bye.
I do have one question, Dr. Chia.
Oh,
Why-
yes, go ahead. Yeah.
You use an older, you use the raw version of R. Do you don't use RStudio?
I'm quite old. I'm old-fashioned. I'm kidding. So I can use both, but so because I'm so used to this old version. So because a lot of my old stuff were written in this style. So, but yeah, it's easy. Yeah, I can use both. Yeah. So you prefer to use the RStudio?
Yes, that's how I was introduced to it. So that's how I know.
The same. Yeah, you just copy and paste to RStudio. So the same. It will give you the same output. Yeah.
Got it.
Different view actually. Yeah, because yes, actually based on this you can roughly tell my age. I'm kidding. I cannot hide my age by showing you this stuff. All right. So yeah, sure. So if you like, I can next time. Yeah, we can use RStudio.
If this way works for you, that's fine. The windows are a lot bigger in the classic R console than they are in.
Yeah, I can increase this much larger. So I think it's better than the RStudio. RStudio like has very small windows, right?
The smaller windows.
Yes. So this is more so this version has, although it is old version, so it has a more degree of freedom. Yeah, so for me, they changed the window size. All right. Okay. Any other questions? Very good. All right. So then see you in the afternoon or next week. Bye-bye.